Looking into space is looking into the past. But when we look back, we are blind. For centuries, we assumed these barriers were permanent. Our models were built on what we could not see. So what if we were wrong all this time? Christmas Day 2021 became one of the riskiest moments in the history of science. After decades of planning, the James Webb Space Telescope finally launched into space.
From a tropical rainforest to the edge of time itself, James Webb begins a voyage back to
The project was delayed again and again. Politically, it survived only because 3 agencies refused to let it fail. Webb cost nearly $10 billion and involved NASA, the ESA, and the CSA. Webb would travel far beyond the moon to a quiet point in space called L2. There was no backup plan. Most telescopes see the universe the way we do, using visible light. It fails when the light becomes too faint or too stretched to detect. Webb was designed from the beginning to see infrared light. Infrared is what remains when visible light is pulled apart by distance and time. As the universe expands, light traveling across space gets stretched, shifting out of the visible range. This effect is called redshift. Infrared light also slips through cosmic dust. The thick clouds that block star-forming regions in visible light become almost transparent. This is why Webb can see further back in time than any telescope before it. By July 2022, the Webb was fully operational. By 2025, the telescope had completed over 860 scientific programs. In just a few years, it collected around 550 terabytes of data. That is more information than the Hubble Space Telescope gathered in 35 years of operation. This volume of data is a gift, but it is also a problem. The more you see, the more chances there are to misunderstand what you are looking at. And if it is, some of our most trusted ideas about the universe may need to be rewritten from the ground up. Neptune glows a deep blue, calm and distant. But when Webb looked at Neptune, it appeared dark. This happens because methane in its atmosphere absorbs most infrared sunlight, leaving very little light to reflect back. With the planet itself dimmed, other features suddenly stand out. Webb revealed Neptune's faint rings in incredible detail. High-altitude clouds also come into view. Webb also confirmed the presence of 14 moons orbiting Neptune. These are the clearest images of Neptune's system ever taken. But on August 6th, 2025, Webb turned its attention to something moving through our solar system. It was a comet called 3I Atlas. Webb broke the comet's light into its basic components. The comet was packed with carbon dioxide and water vapor in extreme proportions. In fact, the ratio was among the highest ever measured in any comet. The comet was not born here. It formed around another star, inside a different planetary system, long before drifting into interstellar space and eventually passing through ours. Webb did confirm that planetary building blocks are universal. Over the past few decades, astronomers have discovered more than 6,000 planets beyond our solar system. These worlds, called exoplanets, come in every size and shape imaginable. But almost all of these planets were found indirectly. Just over 4 light-years away lies Alpha Centauri, our nearest stellar neighbor. It is a tight system of 2 sun-like stars orbiting each other. For decades, astronomers suspected planets might exist there, but they could never prove it. The 2 stars shine intensely and sit very close together. Their combined glare overwhelms anything nearby. Any planet would be completely lost, buried in brightness. Using its mid-infrared instrument and an internal coronagraph, Webb was able to block the starlight. Even with the light blocked, faint traces remained. Scientists had to carefully subtract the leftover glare from both stars. When the data finally cleared, a small point of light remained. That point may be a gas giant roughly the size of Saturn. Even more surprising, simulations suggest it likely orbits within the system's habitable zone. The universe did not just give us a new planet, it gave us a new sense of possibility. Right next door. The pillars of creation are some of the most famous images ever taken of space. For years, they shaped how we imagined star birth. In infrared light, the dust that once blocked our view becomes transparent. Thousands of newborn stars appear, scattered throughout the pillars and beyond them. Webb also reveals motion. Thin jets of plasma shoot outward from forming stars, slamming into surrounding gas. Shockwaves ripple through the clouds. Hydrogen molecules glow as they are energized by violent collisions. The tops of the pillars seem to pulse with activity. Radiation from nearby massive stars eats away at the dust, reshaping the columns over time. The cosmic cliffs sit at the edge of the Carina Nebula, thousands of light years away. In the infrared, the cliffs appear active and restless. Intense radiation from massive young stars just beyond the ridge pours into the nebula. This radiation does more than destroy. As the outer layers are pushed back, dense pockets of gas are compressed. Inside those pockets, new stars begin to form. The same energy that tears the nebula apart also triggers creation with it. This is what scientists call a feedback loop. For the first time, observation matches theory in real detail. Far from the bright center of the Milky Way, in a quiet region called Sharpless 2284, Webb found something extreme. Hidden inside thick clouds of gas and dust is a protostar still forming. It already weighs about 10 times more than our Sun. Massive stars are rare, and they form quickly. But Webb revealed something even more dramatic. This young star is launching enormous jets of gas in opposite directions. These bipolar outflows stretch across nearly 8 light years of space. To put that into perspective, that is almost twice the distance from our Sun to Alpha Centauri. The jets are blasting outward at hundreds of kilometers per second. The result is a pair of glowing lobes, like a cosmic announcement that a star is being born. The jets seen in Sharpless 2284 place this object in a very rare category. Astronomers classify it as an extreme Herbig-Haro object. These objects form when fast-moving jets from young stars slam into surrounding gas and dust, creating bright, glowing patches. There is another crucial detail. This star sits in a low metallicity environment. That means the region contains very few heavy elements, anything beyond hydrogen and helium. Planetary systems are shaped early. 625 light-years away lies a young system known as CTHB. At its center is a star still surrounded by the leftovers of its formation. Webb detected a dense ring of gas and dust surrounding the planet itself. This structure is called a circumplanetary disk. Circumplanetary disks are believed to be where moons are born. Long ago, Jupiter had one. From it came the Galilean moons. When scientists analyzed the circumplanetary disk around CTHB, they found that the disk was rich in carbon-based molecules like acetylene and benzene. The disk surrounding the host star was rich in water vapor but contained very little carbon. Two regions, formed from the same system, showed opposite chemical profiles. According to older models, material was expected to mix evenly as planets and moons formed. In 2024, James Webb turned its gaze toward 19 nearby spiral galaxies. The soft blue regions mark older stars that have already lived most of their lives. The reds and oranges trace thick clouds of gas and dust winding through the spiral arms. This is where stars are still forming. When massive stars die, they explode. Over time, these explosions carve vast bubbles into their host galaxies. Webb reveals these hollowed regions in striking detail, shaped by ancient supernova that pushed gas and dust outward with enormous force. These bubbles are edges that glow where compressed material piles up. Star death triggers star birth. These observations change how we see galaxies. There is a hard limit to what light can show us. This boundary is called the recombination era. It marks the time when the universe was about 380,000 years old. Before that, space was too hot and too dense for light to travel freely. In the early universe, charged particles filled everything. As the universe expanded and cooled, particles combined into neutral atoms. For the first time, light was released. This is the wall of light. Beyond it, light carries no information. When a massive object sits between us and something far away, it bends space itself. This effect is called gravitational lensing. The galaxy cluster RxJ 2129 is one such helper. Its enormous mass curves space-time around it. Light from distant galaxies do not travel straight anymore. It stretches, bends, and brightens as it passes through this warped region. RxJ 2129 acts like a natural magnifying glass, boosting Webb's reach far beyond its normal limits. This trick does not create new information, it reshapes existing light. Sometimes light takes more than one path to reach us. When a supernova explodes behind a massive galaxy cluster, its light can be split by gravity. These images arrive at different moments. By measuring how long each image takes to arrive, scientists can calculate exact distances across the universe. These measurements help refine the Hubble constant. The JADES survey was designed to push James Webb to its limits. As the universe expands, light stretches with it. The farther a galaxy is, the more its light is stretched. This stretching is called cosmological redshift. A higher redshift means older light and greater distance. Webb sees galaxies whose light has traveled for over 13 billion years. One galaxy, JADES GS Z140, stopped everyone cold. Webb measured its redshift at 14.32. That means we are seeing it as it was, only 300 million years after the Big Bang. This galaxy is too massive. According to existing models, the universe was still young and chaotic at this time. For a galaxy to shine this brightly, it must contain a large number of stars. Time, it seems, was used very efficiently. Modern cosmology is built on a framework called Lambda CDM. It predicts how matter clumps, how galaxies grow, and how fast structures should form. Webb is seeing the opposite. Galaxies like JADES GS Z140 are forming stars at extreme rates. They are converting gas into stars far more efficiently than predicted. In 2007, a strange idea entered cosmology. What if the first stars were not powered by nuclear fusion, but by dark matter instead? These objects were called dark stars. If dark matter particles can destroy each other when they meet, they would release energy. That energy could heat a forming star from the inside. Our models assume fusion turns on quickly and dominates star formation. Dark stars challenge that assumption at its core. If confirmed, it would change how we understand the first stars, the first galaxies, and the role dark matter played in lighting up the universe. But what do you think? Let us know in the comments below. And if you want to know more about the other side, don't forget to check out the Artemis 2.